Okay, so for today's class, I will continue the chapter 5.3. This is the fundamental theorem of calculus. And then the half of the class, we can discuss if you want to review your preparation for your midterm. Okay. So as I mentioned in the previous courses, that we need something to connect the derivative and integral, and that is what we call the fundamental theorem of calculus. And to begin the theorem, we could start with this. So this theorem is applied for, like taking this example, we have a random function, this f of x, from the initial value a to the end value b. We have this, and of course in integral you could find the area under the curve, right? But now what we want to do is we are going to take some point in between this a, b, and make this point as a variable. So we could put x in every point between a and b. So we could take this area under the curve as another function. Let's say a function g. Okay? Function g. So function g is from a to x. X is variable. And then we need to determine another, let's say the t will be a dummy variable. So it's like to distinguish between t and x. So we have two variables here. So we have these expressions, the integrations from a is a fixed point, to x is variable of f of t dt. And this is another variable. So this expression can be solved. First, you can solve through the f of t, and then later on you just plug in this x and a. That will be the integrations. But what's interesting on this expression is if we derive this with respect to x. If we derive it with respect to x, we are going to look the expression as a function of x, the original function that we are going to evaluate here. So the first derivative of g will be f of x. Okay? This is very important. This is what we call the fundamental theorem of calculus. This is, I think, part 1 fundamental theorem of calculus. Okay, let me check. Okay, now let me take a new page, and let me take here. Okay. As for example, just for illustrations, if you take the second figure here, we want to try to approximate the area. Okay? What will happen is if, for example, if we want to take, let me write, the general formula is this. So if we take, for example, from this case, for the second figure, if we take g of 1, this means that we are going to approach from 0 to 1 of f of t dt. And basically, what we see here is this is a triangle. So I think it's easy to approach. So we see that it will be half multiplied by 1 multiplied by 2. It's 1. Okay. And if we look at g of 2, which means that this is integration from 0 to 2 of f of d dt. So we are going to look at the triangle and also the rectangle here. So we are going to plus the first area and the second area. So we are going to write down plus 1 plus 2 by 2 multiplied by 1, so it should be 3. And you could also do the same thing, so on and so forth. And let me just make the conclusions with some approximation, of course, that perhaps this is how it looks like. This is just a reminder that when you have the area below the x-axis, it goes to be a negative value. Okay. How we get this is just approximation using the just a normal integrations. Okay. Let me give you directly the definitions. So first definition is this. We already discussed previous page. The second definition is this. So this is part 1, this is part 2. Okay. This second part, or the fundamental theorem of calculus, is if the capital F is the antiderivative of this f, the small f, then if you have integrations from a to b of the f of x, you directly take the antiderivative and then take the n value and then minus the antiderivative of the initial value. And of course, it will end up with the same conclusions, that is the f prime, this is the antiderivative prime, the first derivative of antiderivative, it will be brings back the original function f. It's the same thing with this one actually. I think if you would like to write with the same notations, you could also write g as capital F if you want. So you have it's actually the same meaning, just different expressions. One conclusion from these two connections is every continuous function has antiderivative f. And you could see that we could write down this expression. We could say the second part of the theorem is also, we call this the net theorem. Okay. Okay, let me write in a new page another approach that we can take by using the definition of in limit derivative. Okay. So if you remember, in the derivative, in the beginning, we have these expressions. Limit. Or we could write in different form as well. Forget the limit. Okay. Now, the same with the fundamental theorem for calculus, we could approach through our derivative definitions, particularly for the left one here. So if we have if x and x plus h are on interval, let's say AB, and then we make sure that the capital F is continuous on AB, differentiable on AB. Then, according to the fundamental theorem of calculus that we established in the previous page, we could write that if we take the capital F x plus h minus f of x, we could transform these two into our integration form. So first is from a to x plus h, f of t dt, okay, and then minus same a, but now it's to x of f of t dt, okay. Okay, remember that x and x plus h in our approach in the derivative, when we learn derivative, h is just some additional length from x. So we could actually separate this integration, become a to x and x to x plus h. Okay? So we could separate the integrations. This becomes a to x and then plus x to x plus h. Okay. Now you will see that we have the same integration that we can cancel. Okay. 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 And then if we divide by h, we will have 1 over h integrations of x
to x plus h of f of t dt. And we need to assume that h is a positive value, and of course the f is continuous on the interval x to x plus h. Okay, let's state this as equation 1. Let me make clear here. Okay, why we need this expression? Because this expression is basically, if we take the limit, that will be our definition or derivative. Right? If we take limit as h goes to 0. But let's just take this expression as equation 1, and we are going to see how we are going to use this expression in another theorem. Okay. Okay, I'll maybe to give you more illustrations. This is actually what is going on within this. Okay. So actually, what we have here, this x to x plus 8, is just this rectangle here, okay, that we are going to approach. Okay. We want to approximate this area under the curve, okay, on those small rectangles. Now the next theorem, we call it extreme value theorem. Okay, to begin with this theorem, let me put the picture, this picture. If you remember the comparison theorem in the previous page, the comparison theorem is having some value, this m value, and a small m here. If you could see if we can between the small m and the capital M, we could have our comparison theorem, okay, within these two value. So first consider that suppose there are two variables u and v on the interval of the x and then x plus h. Okay. So f of u is m and f of v is the capital M. So we say that this will be the local minimum value, or in the interval we say this is a minimum value. And in the interval, this will be the maximum value. And we start by taking the comparison that our function is in between the small m and capital M. Okay. And then we take the integrations because we want to compare the area. So the area in between here is between the area of this the small m here and the capital M here. So if we take maybe let me write the original comparison theorem, and then we can exchange some value. So this will be b minus a. This is a to b. This is the original comparison theorem. And then we change the expressions according to our x and x plus h. So a will be x, b will be x plus h. Okay. So we are going to have x and x plus h, ft dt. Okay, now it's become t. And then the b minus a is actually h, right? It's actually h like that. And then all these expressions, we are going to multiply with 1 over h. And now we can see that it's going to be m less equal of 1 over h, x plus h, f of t dt, and this is less equal of capital M. Now we came to this conclusion, which reminds this expression with the previous expression, right? We have this 1 over h, integration from x plus h, f of t dt. The next thing what we're going to do is we're going to take the limit for all these three inequalities. Okay. We can exchange this m with the, since m is function of u, we could change this as, so we take the limit as h is going to be 0 of our f of u and then take a limit as h goes to be 0 of the we can exchange this the middle expression with this f x plus h minus f x over h. So it's going to be, okay, and then less equal limit h goes to 0 of f of v. Now, as the h getting closer to 0, what will happen? If this h is getting 0, phi will be equal x, right? And of course, u will be also getting closer to x. Okay, so we could say that as h getting closer to 0, phi will be getting closer to x, and u also getting closer to x. So we could say that limit of f of u as h getting 0 will be equal to f of x. Let me write here. So limit and the same thing with the phi.
And then, by the squeeze theorem in limit, the limit inside here will be equal to f of x.
Let me resize this part first. And then by squeeze theorem, limit as h getting 0 of this antiderivative x plus h minus f of x divided by h, this will be equal to f of x. So the conclusions from all the proving is still what we have in the beginning, that if we have some integrations from a to x of f of t dt, this will be resulting its original function f of x. Okay. So what does it mean is,
If we take this f, we take integrations, we take derivative,
this will going back to f of x. Or we say f prime x is f of x. Oh, forget ddx in the front.
So to prove all this is taking the comparison theorem in the previous section. This is the comparison theorem. And then exchange all the a, b to x and h. And multiply with 1 over h, and you will receive this. And looking at this part here, this is, we can rewrite as this fractions. Taking the limit and take the squeeze theorem. Okay, that proving the middle part of all these expressions will equal to f of x.
But of course,
This is for the definition only. There will be some applications for how to take this fundamental of calculus in practice. For example, sometimes the function can be written as in the integration form. So if we take the, like for example, this is a function. Although it has the integration, it's a function because it goes from a to some variable. So we can say it's also a function. So basically this chapter will take more
all the differentiation part in chapter 3, the techniques. But what we are going to derive is the integral. Okay, let me give you a couple examples, perhaps, to see how we can apply this theorem. Okay, so for example, if we want to compute, okay, so if let me check, find derivative of gx equal okay. Remember, to have the derivative, okay, we need to make sure that the inside here is continuous. And of course, this is a continuous function, right? So we could say that f of t is continuous. So the derivative, if you remember how the fundamental theorem of calculus works in previous page, is basically, if we derive the integral form, we will have the original function f of t. And basically, in practice, what we do is we are just substituting this x inside this t. Okay. So we are going to have that g prime x is square root of 1 plus x squared. Now, what will happen if I change the equations? For example, let's make hx. And instead of just x, we are using from 0 to 2x. What will be the first derivative? Yeah, but what I want to emphasize on this hx is we are going to focus on the chain rule that might happen. Okay. So first, if we could say that this 2x as
another variable. Let's say we exchange 2x as u. We substitute with u.
So let's say this part here, we take the equal to some u. So let this u is equal to 2x. Okay. So instead of
taking h prime x as d dx, we are going to have a chain rule because we have u now. So we have some dummy variable u in between for finding the dx. So we will have d dx and we need to multiply with some du.
Okay. We multiply with some du. So we could write this as d du. Okay. Still the same inside, 1 plus t squared dt. Okay. And then we need to multiply du dx to
get our original d dx.
Or let me write with 2 steps to make sure that you understand. The original expression for h prime x is d dx
So basically what we are doing here is we exchange this 2x with something that is perhaps more simplified, u, and then taking this d dx and makes them into a chain rule and becomes du, and then we need to multiply with du dx to make this into d dx. Okay. So basically, this part here is the same thing as we did before. So we just take this u inside, practically just substituting this u into this t squared. And we get the first part. And the second part, what is this? This is the derivative of u with respect to x. Okay?
So we could have here du dx is just 2. So perhaps we start with the substituting this and makes this into 1 or square root 1 plus u squared, but u is 2x. So let me write within the x expressions. This will be 4x squared and multiply by 2.
And perhaps if this aspect of substitution may be a little bit confusing, let me write in a different way.
Let me write in, let's say we have a gx equal, this is, let's say from 0 to h of x.
Actually, you can take this from any constant. If you remember the previous page, it doesn't really matter, right? Because it will cancel, right?
So let's say we have from 0 to some function h of x. And here's the f of t dt. Now from
what we have here,
actually, this is just, if we take derivative, this will be f h of x and then multiply with h prime x.
I think better to visualize this better than this one, right? But this is also, I think, important because this is, I say,
well, it's not necessary to be 0 here. It can be from any constant. Let's say a is any constant. A is constant. So if we have another example,
Q. Okay.
so this will result in secant x with power of 4 multiplied with 4x cubed. Or if you would like to write in more detailed, we could take this and make it into d du, and then take it from 1 to u secant t dt, and multiply with du dx. So we will have secant u multiplied by du over dx, and this is the result. So let u equal x. Okay, so this example is for the at least for part 1 of the fundamental theorem of calculus. The part 2 is more direct, because it will evaluate the whole numbers. So if we have integration from 1 to 3 e to dx dx, let me just finish this. This we can say f3 minus f1 or let me just take another example, 3 to 6 dx over x. We could write the 1 over x as in antiderivative, if you remember. This is, we could write f6 f3, so ln 6 minus ln 3, or this will be ln 2. Okay, okay, we will have a break.
Okay, as a discussion for this calculus preparation for your midterm exam, this is what we have in your exercise. I forgot to attach the answer. I will attach after the class. Okay, all the whole answer for the exercise chapter 4. But what I want to emphasize on this numbers is you will likely to have this similar question, so you need to prepare maybe if you want maybe a ruler, but it could be like it could be drawn without ruler also, as long as your drawing is, I think, as long as it's proportional, I think it's still okay. I don't really need the exact like value, as long as you logically make sense that it's true, I think it should be okay. So what I want to emphasize from here is also the domain. The first part here is really important. The domain, intercept, and defining the limit for the asymptote is important. It is, I think, to draw our graph.
Like the graph is this, right?
If we have designed our asymptote first, we would like to know how the function will behave. Okay?
the other part to complete that is to know whether when the function is increasing, decreasing, and when is having the concavity change, or maybe having some concave upwards, concave downwards. Right? So the first part is finding the design first, the asymptote, and then the first derivative, second derivative, finding the increasing, decreasing concavity. Okay. Okay. I would like to start with some exercise, okay, just to remind you how to solve that. I think I've prepared some. Okay. Let's start with this. Okay, giving you some minutes to try. You can check the limit first, and I believe it will have like indeterminate inside indeterminate forms. No, indeterminate multiply with another. Or we could say, because if we tilt the infinity inside, it will be 1 to the power of infinity multiplied with infinity. So indeterminate and multiply with, and then become the multiplication of indeterminate forms. So it's kind of all in all is indeterminate forms. The key is the same. The key is the same for all aspects. If you have any functions and we have a power with another function, basically either in limit, either in derivative, what you are going to do is you need to make sure that power can go down. Okay. So perhaps we could take this and maybe to make it simplified, maybe we take y as this expression, and then perhaps we take ln. Okay. Okay. So we're going to have y, and then we have, let me write one by one, ln, and then plus ln e power of x. This part will be x squared ln 1 minus 1 over x, and then this will be plus x. Okay. And then we take the limit. I think it's still indeterminate forms, and we need to make sure that we could make some expression that involves 0 over 0 or infinite over infinite. How about we could try to make this ln and then we could take this ln x minus 1. If we take the ln 1 x plus x, if that is the case, we still have infinite over, I think infinite. Oh, let me maybe let me check for a while. To make sure if there is any mistake in my questions. Oh, I think we could take this. If t is equal 1 over x, I think we can solve this. So change all with t. 1 over t squared ln 1 minus t, and then plus 1 over t, and then plus t, right? Okay, it's 0 over 0. Okay, 0 over 0. And then take L'Hopital. So this will be negative 1 over 1 minus t plus 1 over 2t. And then this will be we solve this negative 1 plus 1 minus t, so cancel minus t, so minus t over 1 minus t and 2t. So cancel, and we get the result is negative 1 over 2. But remember that this is still the L and Y. So Y is E with power of negative 1 over 2. So 1 over square root of E. Yeah, it's difficult. I almost forgot how to solve it.
Yeah. So I think the key is this part. Okay? The key is this part. So sometimes when you have equations including, like for example, 1 minus 1 over x like this 1 over x, if you see that it goes to infinite number, we could try to express the limit in different form using this t is equal 1 over x. And when we have this x equal or getting closer to infinity, the t is getting 0. So we can change all the expression with t to make our calculations better. With this change variable from x to t, we could see immediately that the form's getting 0 over 0, in which we can apply our L'Hopital rule. Because I think if you stop here in this term of x, we cannot really do anything about that, because it's not really 0 over 0 or infinite over infinite.
do you think of the question? Good for exercise. Because in one question you have like a limit, the derivative itself, the logarithmic derivative, the indeterminate forms. Okay. Maybe I will write on the right side to take another exercise. Oh, it's too long. Maybe I will write in bottom here. It seems really long, but just try to look first, and then maybe think. If you want, you can try to use a quotient rule, but I'm not suggesting that. I just want to know how you approach it if you have like this complicated problem. So we need to solve this into the limit. Okay. So let me give you an illustration on how we can solve this. The first thing is we take the limit. Remember that if we take the limit as x to a, this is our definition of derivative in limit. This is equal to f prime a, right? So if we would like to have f prime 0, then we need to change a into 0. Okay. So that's the first thing we could write. So limit, or maybe let me write into f prime 0 is equal limit as x approach 0. Okay, so you need to solve this limit. So for starter, to take the f0, we could just plug in 0. So f0. So this will be 0. This will be 1, as this will be 0. This will be another 0. This will be 1, but it's all 0 aside from this 1 here, 3. So 0 by 3, 0 divided by 3 is 0. So we could say that it's 0. So we're just having the limit as x approaching 0 of f of x divided by x. Okay, now to solve this, maybe we could take it into two separate limits. Okay. So first is taking the limit as x approaching 0. Maybe first taking all the secant, the bottom part. So 3 secant squared x plus x cubed sine inverse x. Okay. And then multiply with the limit and take another limit here. X goes 0, tangent 2x, cosine inverse x, plus ln 1 plus x. So although sometimes the definition of the derivative in limit is really not applicable because we have the techniques that we can derive directly, but for some cases like this one, we might need this limit definition to work our derivative. Okay, now we can solve one by one. I think we could say for sure this part, I think if you substitute it's okay, right? It's a constant. So we can say it's safe here. So we need is to solve this part. If we look here, we have the tangent. Okay. I think I haven't really told you about the tangent, but the tangent has a property similar with sine in limit. So if you remember, if we take, let me write here notes. If we take limit as x approach 0 of sine x over x, this will be equal to 1. Okay. And this will be also correct for tangent, because for cosine doesn't really affected by this part. And we have, if we take the tangent, if you can also prove this by yourself, that this is also equal 1. So if we have the tangent to x, we could take this, let me write here. First is this, and then the second is the ln. Oh, I forgot to divide by x, because we have x here, right? So we need to divide by x. Let me divide by x like here, and x here. Okay. Now, to make this tangent x over x true, equal 1, then the tangent to x, we need to multiply by 2 and multiply by 2. To make it, this can be cancelled and it become 1. So we could take that. And the last part here, we could just do L'Hopital rule. We could just do L'Hopital. It's 0 over 0. So we could have 1 over 1 plus x. 1 over 1 plus x. Or just 1. Okay. Oh, wait. This part is become 1 over 3, right? 1 over 3. So so 1 over 3, multiply whole thing here. When x is 0, the cos inverse 0 is pi over 2. This one is, you can cancel this, and we can 2, pi over 2, so it becomes pi plus 1, pi plus 1. So we could have here pi plus 1 over 3.
Where do we get 1 over 3?
From here. From the secant here. We just plug in 0.
Okay.
Yeah. This goes. Yeah, we take the 0 in secant is 1, right? Secant 0 is 1. Sine inverse is a 0, so 1 over 3. So 1 over 3 here. So this tangent to x, we can solve by multiplying with 2 over 2. So tangent 2x over 2x is becoming canceling each other. Well, you could always do the L'Hopital rule here, but I think this is more simplified. I think it's also 0 over 0 that you can L'Hopital. You can do L'Hopital. Yeah. What do you think about the question? Quite bizarre. I could say quite bizarre. I also need some time to solve this. It's one of questions from, I think, some midterms from University in Taiwan. They have this question. I also shocked when I read, wow. But I think it's good for exercise. Good for exercise.
Just derive it.
Huh?
Just derive it.
I think if you have limited time, you will have more mistakes than this. Actually, because you can see some after the program rule. There is a certain rule, but inside the quotient we have the program rule, but it has also the inverse trigonometry. But I think you can also check if you use the directly derived. You can also check if you have like. I think it's also a good exercise for the techniques. For the techniques itself, I think it's also good. But if you consider the time limit, I think this one is maybe more simplified and you can avoid a lot of mistakes. You can avoid
If it's not a
well, it depends. Depends on the question.
deriving is not the problem. Simplifying what you derive is the problem.
Ah, yeah.
It's something else.
Yeah, sometimes you derive and maybe it's too massive. Yeah. This
Maybe x approach x approach 0 and alpha sides can be 0 or
this cosine inverse
it can be 0 or pi.
pi over 2.
Pi over 2.
Pi over 2. So it's pi over 2. I maybe you need to write. This is pi over 2. This is 2.
This is asking for the angle. The angle or
Yeah. We had some guesses that would like to have some survey, right? Maybe they will explain. Okay, where's this for a while? If you need, maybe if you want to talk to the
那个我们是另外系3年级的学
Because
生，
we're
然后我们
conducting surveys
现在
in
那
the
个毕
future,
业专题，我
and
们
we
做
want
个
to ask you
先
if
修
you
班
have
有
time
关
for
的研
us
究
to。
然后我们想问，
interview in the
其实我们
Okay,
的
okay,
Yeah,
sure.
so
那
we'll
个
contact you the
主
time.
要
Yeah.
那
It's
个
going
主
to
要
be
要研究对象是
begin.
台湾
I
的
think
学
it's
生，然后
going
我
to
们
be
研究
in the
有
next
参加过
semester, the beginning of
EMI
next
全球
semester,
版跟
or
没参加
Yes,
过的
yeah, on the
那
interview.
个
Oh.
在 EMI
So
课堂
I
上
will
的
just
学
contact you.
Yeah,
所以我
just
们
just
想要
assign me.
调
Okay,
查一下
thank
有
you.
没有参加过，就是这个暑假语言中心办的全球版，有人有参加过吗？我有。好，有参加过，帮我举手一下。只有一个，好。只有一个，好，那这样就可以没关系。然后我们可能在15、16周，可能会有一个问卷，可能会有个问卷，就都还不确定这样。然后那个问卷可能大概只要5到10分钟填写而已，就大概是这样。好，谢谢大家。
Okay, maybe one more example. Okay, one more example before we close. There will be no feedback questions for today. Yes. I believe the first one to complete the first arithmetic, I hope you still get it. The second one, although it maybe it'll take time to complete, maybe it will be really long. But I hope the first one you can get it. The first one. For a while, you can check implicit. This type of question would likely to be appear in an exam tomorrow. I mean the techniques. There's the techniques. At least the techniques to solve it. And then there will be no related traits. No related traits in the question. Yeah, if I read the question maybe too many, and I erase them. So my suggestion for tomorrow, maybe bring the ruler, and maybe if you have more than one color pen, you can bring. Maybe it will help. If you have blue and black, maybe it will help. Especially for sketching a graph. That will be for sure will be the question. So at least for that question, you need to be optimized. Okay? It's optimization. You need to optimize. So I think because we just need to put the x equal 1 and y equals 0. So from here we get the conclusion that x equal 1, when x equal 1, y is 0, right? So when you have, maybe you derive and then you have like long derivative result, you could just take the x equal 1, y equals 0 into the equation. And you can solve it. I think it will be helpful because y is 0. So sum of the part will be 0, right? So let me write the results first. So it will be 2x cosine xy minus x squared sine xy, and I need to multiply the chain rule, the y plus x dy dx, and then we're going to write here. This is long, and plus e y squared 2y dy dx, and then minus 2 plus dy dx. So you could exchange all the terms. I think you can look at the 0. So this will be 0. So cosine 0 is 1. So this is 2. This is 1. This is 0. So whole thing is 0. No need to compute. So this is 0. No need to compute, right? Easy to compute, right? Okay. So it seems like very sometimes maybe few students, because they not really pay attention to the question, they solve this first and wasting time and then write dy dx equal to some formula. Just stop here and then just substitute the number. Okay? It will be efficient and effective. And we could see that the dy dx from here is equal, when x is equal 1, is equal 0. You can check the results. Now I hope you can also try for the second one, finding the second derivative. And although like from here you derive one more, maybe like longer, when you take the x equal 1 and y equal 0, you will also get the same similar structure. So I will end the course up until here. See you tomorrow. Okay. So hope you can get best results. Okay. Okay, so at least sketching the graphs. Okay, so you could maximize on those parts. It's a huge point on that. A huge point on that. So please maximize that part. Because I'm not sure for the other part you can do. But I think half of the questions you should be able to do. Okay, I expected at least half. The other half is you could like try your best effort.